Before we get started on the stuff that I want to talk about today in terms of Chapter 16, I want to start by asking a question about how we would go about making this disubstituted benzene from benzene using electrophilic aromatic substitution reactions. Looking at that, what do you see as the main problem? Why is it a problem? Okay. Part of the answer? What else? They are meta to one another, and why is that a problem? The two groups that are on there are what? Ortho-para-directors, right? So that seems like a problem. Nonetheless, you can purchase that molecule, and it's not that hard to make. How do we solve this problem, Matthew?
You first use a meta-director and then substitute that from...
Okay, so how would we do that? So we're starting with benzene. We need to have a meta-director. So which group am I going to put on to do that, that's going to serve the purpose ultimately that I need? Probably a ketone, right? And do Friedel-Crafts acylation. What would my reagents be in this particular case? All right, I need aluminum trichloride. What else do I need? Ketone with a chlorine, that's known as what? It's not a ketone. Ketone is a carbonyl with two carbons, but this is an acid chloride. Which acid chloride do I need? How many carbons do I need? I need two, right? Because I've got two carbons in my product. So we'll put that on first. That gives me a meta-director, right? Now what do I do? With what? All right, so I'm going to put the bromine in. What do I need for that? Iron tribromide. And what else? Bromine, yeah, just liquid bromine. And that's going to put in my halogen. And so now I've got a carbon group and a bromine that are meta to one another. But that's not my final product. So now what do I do? I'm going to reduce it. How am I going to reduce it? Pardon? Okay, I can use the Clemmensen reduction. Will be a perfectly good way to do that. What are the reagents for the Clemmensen reduction? You're tired of talking? Okay. No, KMNO4 hot is not going to do a reduction. That'll do an oxidation. Pardon? Zinc, mercury amalgam, and HCl will be the Clemmensen reduction. But I heard somebody mention in the Wolff-Kishner reduction conditions, and what would those be? Yeah, that's right. So either one of those would have worked just fine here. Now, Gabby had mentioned using some hot potassium permanganate. What's going to happen? Where? Which carbons? I got a lot of carbons. Okay, so here? That's right. It'll oxidize that particular carbon atom to a carboxylic acid. The other carbon gets wasted as carbon dioxide, actually. So it's a great way of making benzoic acids. Do an oxidation process. Okay. Does that all make sense? Electrophilic aromatic substitution reaction, good stuff. I really like it. It's going to be on your next test a lot. And it's going to be more than just putting on a single group. You're going to need to know what reagents are required, what the electrophiles are. You're going to need to know the general mechanism, and you're going to need to know directing effects. Things like this. Okay? What would have happened, let's say Sarah decided to do this exact reaction to here, but she misread her notebook and decided to put the bromine on first, what would happen? What would the product have been? That's right. So she did the bromination first by mistake. Sorry, Sarah. Not that she would make a mistake, but it just happened. Right? And then she did the second step. You would expect a mixture of both ortho and para substituted molecules, right? And which one of these would have been the major one, you think? Ortho or the para? The para. Very good. So she would have actually used the right combinations of reagents in each individual step, but getting them out of order gives you exactly the compounds that you're not looking for. So it's not just knowing all of your reagents and the mechanisms, but also knowing which order and which to put them in, where you're going to start and where you're going to finish. Okay? So, a lot of stuff there. Today we're going to start talking about aldehydes and ketones. We're starting to get into this part of Organic 2 where there's going to be a lot of repetition. We've talked about aldehydes and ketones before. We've made aldehydes and ketones before. How do we know how to make aldehydes and ketones already? Let's start with aldehydes. How do we make aldehydes? Oxidation of what? What alcohol? Any alcohol? Primary alcohol. And use any oxidant? PCC. That's right. And we know how to make ketones, right? We can oxidize secondary alcohols, right? So on and so forth. We've already talked a little bit about that. We'll refresh our memory a little bit on a lot of this. I'm going to expect you to learn the nomenclature on your own. We're going to talk today about some properties and spectra and some reactions, and look at how some nucleophiles can react with aldehydes and ketones, okay? So you all know that aldehydes and ketones will react with nucleophiles. We've already done that chemistry. What was the nucleophile that we were using in the previous chapter? Pardon? Grignards. That's right. And so we were making carbon-carbon bonds. A Grignard plus a ketone gives me a, what does it give me? What alcohol? Tertiary alcohol. A Grignard plus an aldehyde gives me a secondary. That's right. So keep that all in mind, right? And so as we look at ketones and the various different flavors of aldehydes, you can see that ketones are more sterically hindered than aldehydes. And so the ketones are actually less reactive than aldehydes towards nucleophiles. Having said that, unless the R group is really, really big, ketones and aldehydes are still both very reactive towards nucleophiles. Okay? And so it's true that the ketone is a little less reactive because you've got more steric hindrance, and those two R groups are kind of getting in the way of the incoming nucleophile. Okay? So if we look at some of the physical properties, if we look at boiling point and melting point, you can see that for an alkane, we're just dealing with van der Waals forces, but in this case we've got an aldehyde. Not only do we have van der Waals forces, but we also have dipole-dipole interactions. And so you can see a substantial increase in the boiling point. And then it's going to be, since we don't have hydrogen bonding in the pure state of an aldehyde or a ketone, it's going to be somewhere between alcohols and alkanes. And that's kind of what you see here, right? Solubility, we know that aldehydes and ketones are going to be soluble in your typical organic solvents, things like that, chloromethane, hexane, ether, so on and so forth. However, some of them can be soluble in water. A ketone or an aldehyde that has 5 or fewer carbons per aldehyde or ketone group typically will exhibit solubility. Common example is your fingernail polish remover, acetone. It will completely wash off in water, right? And that's because it has 3 carbons and a ketone, and it can form hydrogen bonds with water as its solvent. Okay. Recall just a little bit back from Chapter 2, where we were talking about IR spectra. You would expect to see a carbonyl stretch, and that's what we see here, right? We do have an sp2 hybridized carbon that has a hydrogen on it, so we should see that hydrogen in this region. And then we obviously see the sp3 hybridized hydrogens that are in this molecule as well. So when looking at aldehydes, we would expect to see the carbonyl and the sp2 hybridized CH bonds that are present. For a ketone, we're still going to see the carbonyl, but that sp2 hybridized CH bond will be absent. And a ketone and an aldehyde, pretty much so around 1700 if you want to be a little more specific. You can use IR spectra to determine the ring size of a ketone. So if you look at cyclohexanone, cyclopentanone, and cyclobutanone, what do we see as we move from left to right in that series? What's happening to my wave number? It's increasing, right? And it's increasing with respect to ring strain. Okay? So ring size affects the carbonyl absorption. And so if I was to give you these three ketones and ask you to figure out which one's which, you could just go run an IR spectrum and measure accurately the carbonyl absorption and put them in the right order. Okay? So as you increase ring strain, you're going to increase the frequency at which the carbonyl absorbs in the IR. Anybody want to take a guess as to why that might be true? What happens as you move to the left? We go from sp2 to sp, right? And so the bond angles are becoming more close to, yeah, they're getting closer and closer to what you might expect for that. And so you end up with an increased wave numbers as ring strain increases. Okay. Conjugation also affects the IR absorption. So if you look at an example like this, we call this an alpha-beta unsaturated carbonyl because the alpha carbon and the beta carbon are unsaturated. Now we can draw resonance structures, right? So what can you tell me about that carbonyl bond? Should it be weaker or stronger? Why would it be stronger? Why would the carbonyl bond be stronger? The C double bond O. What does the hybrid tell us? It's going to be slightly longer than predicted, right? So does that mean it has more sp2 character or a little more sp3 character? And so sp3, if you remember in the IR spectrum, right, the fingerprint region was sp3, then sp2, then sp, right? So these are moving closer to the sp3 or to the sp2? Or to the sp, I mean, if they're going lower wave number. Getting closer because it's got more sp3 character out of the resonance hybrid. So you can see that in this particular case, this ketone has no resonance stabilization, right? It's just a cyclohexane ring, and it absorbs around 1709. Replace the cyclohexane ring with a benzene ring. Now we can draw resonance structures like we did up here, and you'll see that it shifts quite considerably. Okay, it moves closer to the fingerprint region where all the sp3 stuff is. Has to do with this, with the strength of that pi bond. You can also see the same thing here. Cyclohexanone versus the alpha-beta unsaturated version, it gets shifted lower in wave number. So you can actually get more and more information from IR than what we've been doing in this class so far. That's the take-home message. Okay, you can get an awful lot of information from the IR if you know how to be careful in its interpretation. Okay. NMR is the one that I'm going to hold you most responsible for because it's the easiest to interpret and not have to rely so much on relative arguments like you have to with the IR. Aldehydes and ketones will exhibit both proton and carbon NMR absorptions. The hydrogen on the aldehyde functional group, okay, is highly de-shielded, and so it's going to appear somewhere between 9 to 10.5, depending on what it's attached to, okay? So remember, in the NMR, where do we draw the initial line? At 5, right? And everything to the right of 5 is sp or sp3 hybridized, and everything to the left of 5 is sp2, right? The hydrogen on an aldehyde is attached to an sp2 hybridized carbon. So that's correct, but it's going to appear way downfield, right, or between 9 and 10.5 or so. What else appears in that region? Not 9 to 10. Carboxylic acids, those hydrogens appear that far down. Yeah. Ooh, that was you shot somebody in a dagger eye. No? It turns out that the splitting on the aldehyde will occur. So that aldehyde, if it has neighboring protons, it will get split, but the coupling constant is quite small. Okay? And so the J value is typically between 1 and 3 hertz, which means that you quite frequently have to look very carefully at that peak to see how it's split. You know, a typical triplet you can see quite clearly, right? But if you had a triplet for an aldehyde proton, because it has 2 neighbors, you'll have to really hone in on that and see that. And usually on an exam, I'll tell you it's a triplet if it is. Okay, something like that, because it's hard to see in a normal blow-up. Okay. Now the carbon for the carbonyl, again, you're going to find that somewhere around 200. It's going to be way downfield as well. It's highly de-shielded. You'll find it way down there as well. Okay. So here's an example. We've got propanal. We have 3 unique environments, HA, HB, HC. If you look at HC, you see that that appears pretty close to 10. It looks like a what? It looks like a singlet, and they didn't blow this one up. But if you actually hone in on this, you'll see that it's actually a triplet, okay? Because this proton has how many neighbors? It's got 2 on the neighboring carbon, so it should appear as a triplet. And in fact, if we were able to blow this up, you'd see what would be a triplet. Here we have a quartet for HB. Why is it a quartet? But why is it a quartet? It's got 3 neighbors, but wait a second, it's got another neighbor there as well. So why isn't it appearing as 5 peaks? It is a neighbor. Huh? Yeah. Remember, nearest neighbors are on adjoining carbons. So HB looks like it's only coupling to HA, right? Giving a quartet, but it's also got that neighbor HC, so why is it only appearing as a quartet? It's because the coupling to the aldehyde proton is small. You're not seeing it. It's there, but you're not seeing it. It actually should appear as a doubled quartet. So you get a quartet from the 3, and then it gets doubled because of the other neighbor. It's called higher order splitting. But it's absent in the view here because we're not able to see that finer coupling within the peaks. How about HA? It's a triplet. Why is it a triplet? It just has 2 neighbors. That's right. If we were to look at the carbon spectrum, you can see that we have 2 carbons clearly in the sp3 region for A and B, and we have one that's just past 200, clearly where we would expect to find one for an aldehyde. Now, A, B, and C are all just 1 carbon atom, right? So why is A and B of higher intensity than C? Anybody know why? Shouldn't they all be the same height, the same integration? Well, they are hybridized differently. What else? What did I tell you about carbon spectra? What can't we do? Can't integrate them because the integrations won't quite work out for the way that we're running the carbon spectrum here. Okay, we're not running it in a way where you can get accurate integrations. What's the difference between CA, CB, and CC other than the hybridization? Okay, what else? The number of hydrogens that are attached to it, that's right. And so it turns out that the more hydrogens you have attached to a carbon, the more intense the carbon signal typically is. Okay? And so that's why carbon C is actually only about half the size of the other carbons, okay? Because it only has one hydrogen attached to it. Okay? So here's some examples of two aldehydes. How would you distinguish these two aldehydes from one another in the NMR? What's the characteristic signal that you'll be looking at? Both of them had an aldehyde that integrates to one, right? What can you tell me about these peaks? Might be kind of hard to see. How's that split? That's a doublet, and that's a... What will that one be? How many neighbors does it have? So it'll be a... So that belongs to this one. And this one has how many neighbors? One. It'll be a doublet. So just based on that information alone, you could have identified which molecule belongs to which spectrum pretty easily, okay, by looking at those aldehydes. All right, let's talk a little bit about some interesting aldehydes and ketones, things that you're all familiar with, whether you know it or not. This morning you may have woken up, made your oatmeal, whatever you liked, and you may have added a little cinnamon to it. And in doing so, you added cinnamaldehyde. Okay, it is an aldehyde molecule. It is what's responsible for the odor of cinnamon. You can clearly see the aldehyde peak. This aldehyde, however, is also alpha-beta unsaturated, right? So this is an alpha-beta unsaturated aldehyde, and it's quite aromatic in terms of aroma. It is aromatic as well in terms of the benzene ring, but it's what is responsible for the cinnamon smell that you have in your cinnamon that you add in the morning. Benzaldehyde, a common aldehyde. If you ever walk into our lab when we're using benzaldehyde, I don't think it really smells so much like almonds, but it definitely smells like maraschino cherries. If you've ever opened up a bottle of cherries, you know that cherry smell that you get? You open up a bottle of benzaldehyde, it's almost identical. It's almost like somebody's eating cherry ice cream or something in the lab. Does it? Okay. I've never worked with almond extract, so I don't know. But it's gross. Yeah, Matt.
So is it okay, how would you just like ingest it?
It's actually present in cherries and the nuts. I mean, benzaldehyde's there. You are ingesting it. Do not take a bottle of benzaldehyde and ingest it, okay? But, yeah, I mean, it's present. It's actually used as the in some of the flavorants. Citral, a little more complicated in terms of the number of carbons that you're dealing with, right? But this is that lemony odor that you get from things like lemongrass, okay? All of these are aldehydes that we're talking about. If you happen to like blue cheese, it's a ketone. Heptanone. You don't like blue cheese dressing? It's disgusting? Oh, it's good. Blue cheese is good. Huh? You're a fan of blue cheese? Yeah, me too. I like it. It's good on salads. But the odor of blue cheese comes from a ketone, not an aldehyde. Okay? And so it gives you that odor that you have. Let's talk about some ways in which we can synthesize aldehydes. We've talked about a variety of methods to do this. You're going to start seeing lots of methods really quick, okay, that you're going to have to commit to memory. You no longer have your note card, so you're going to have to know this. You already know this one. You could take a primary alcohol and you can oxidize it to an aldehyde with PCC. Pretty straightforward, right? But maybe you don't have a primary alcohol. Maybe you have an ester. You can reduce an ester to an aldehyde if you're a really good chemist, because it's kind of finicky, using dibal or dibol, diisobutyl aluminum hydride. We'll talk about the mechanism next time, okay? You have to do this at low temperature, minus 78 degrees or colder, okay? Pardon? Doesn't take, it depends on the ester. But a simple ester, no, it doesn't, maybe a couple hours to do it. Pardon? It's not long at all. So you can take esters to aldehydes, and you can take acid chlorides to aldehydes using lithium triterpbutoxy aluminum hydride. Okay, and again, very cold, you can reduce it to the aldehyde. So now you've got multiple ways to make aldehydes, right? You can oxidize primary alcohols with PCC. You can reduce esters with dibol. You can reduce acid chlorides with lithium triacetoxy aluminum hydride at cold temperatures. You can get aldehydes quite easily through those reductions, or at least straightforward on paper. Okay? This third box down here is doing what? We're doing hydration of an alkyne to get an aldehyde. What kind of hydration? Hydroboration oxidation, which gives me what kind of alcohol? Anti-Markovnikov. The first thing that you get is an anti-Markovnikov alcohol, but you still have the double bond. And what did we call that last time? When we were talking about Markovnikov and anti-Markovnikov alcohols. What are we going to get when we add a single molecule of water across a triple bond? What is that? Is that an alcohol? You're close. Alkenol, but we didn't call them alkenols. We called them, we didn't have the alk part in there. We called them enols. We get an enol intermediate. Are they stable? They are not. And what do? What is this process where they go from the enol to the aldehyde? What do we call that? Started with a T. What is it? Pardon? T words? Just keep saying T words. Have I added any new atoms? No. It's just rearranged, right? But it's a rearrangement that has a name. What was that name? We've talked about it. Tautomerization. Tip of your tongue. The tip of your tongue must be this big. Tautomerization. Why did we have to use the hydroboration oxidation sequence? Because we wanted the OH on the least substituted carbon. We wanted that to be anti-Markovnikov, if you will, and then that tautomerizes into the aldehyde. So we can make aldehydes from alcohols, esters, acid chlorides, alkynes. You can make a lot of different functional groups pretty easily if you know how to use your chemistry, right? And so that's hydroboration oxidation to get to the aldehyde. We can get to ketones using very similar chemistries, or at least from the viewpoint of the starting material. If we take a secondary alcohol, we can oxidize it using one of the Jones reagents, for example. PCC will also work, and we get a ketone. We can also make ketones by reaction of acid chlorides with what are known as copper reagents, cuprates, okay? So we take an acid chloride, these organocuprates, and you can get ketones. How do we get an organocuprate reagent? You can buy some of them, but most of them you can't. You have to make them in what's called in situ, meaning we generate them just prior to use. What other atom is up there? Lithium. What kind of molecules do you know about with lithium? Okay, but that's not organic. It's true. What organic compounds that contain lithium do we know about? Pardon? Alkyl lithiums. And it turns out that organocuprates are real easy to make. You simply take an alkyl lithium and you mix it with something like copper chloride, and you will get the organocuprate, okay, through a process that we're not going to talk about. It's an organometallic process, and metal exchange, and a whole 9 yards. What you need to know is that they will add to things like acid chlorides to make ketones. Why can't I use just a lithium reagent to do that? What would happen if Carl took an acid chloride and threw in an alkyl lithium? It will. Ultimately, that'll fall out of solution, but what else will happen? I'll tell you the first step is he makes a ketone. An alkyl lithium will react with an acid chloride to give you a ketone intermediate that what happens then? It continues to react because ketones, we know, react with Grignards and alkyl lithiums to make alcohols, right? Organocuprates do not react with carbonyl compounds like aldehydes and ketones. It has to be extremely reactive, something like an acid chloride. They are much less reactive than the organolithium or the Grignards, organomagnesium, I should say, the Grignard reagents. Okay? So we can make ketones from acid chlorides this way. We can also make ketones from acid chlorides this way, following the Friedel-Crafts acylation reaction that we talked about, electrophilic aromatic substitution. And in fact, I will just let you know that if you have an acid chloride, most people prefer to do this type of chemistry over this type of chemistry. Okay? The only limitation is here you have to have an aromatic ring that you want to put in your molecule. Up here, that's not a limitation. Okay? The only limitation you have to the cuprate is being able to obtain the cuprate. Okay, but you can have cuprates that are aromatic, you can have cuprates that are non-aromatic, and so it's a little more general. And we can also prepare ketones by hydration of an alkyne. What's different between this hydration and the previous one to make aldehydes? What's that? All right, we're not using hydroboration oxidation, so we're going to do Markovnikov. And so the OH is actually going to go on the more substituted carbon, giving us that enol, which then tautomerizes not to an aldehyde, but to a ketone, okay, because it's not on that primary carbon, if you will, for lack of a better term. It's on that secondary carbon. And so that's why you end up with a ketone over a aldehyde. Okay. Now, we already know that aldehydes and ketones can react with nucleophiles, right? We can take a nucleophile and we can have it attack the carbon of the carbonyl, and we can get an alcohol. So if I have an aldehyde plus a nucleophile, I end up with a secondary alcohol. If I have a ketone and I react it with a nucleophile, I end up with a tertiary, right? But aldehydes and ketones can also do chemistry at the alpha carbon. Okay? Because of resonance structures, we can actually abstract one of these hydrogens. These are more acidic than a typical CH bond. And you end up getting what's known as an enolate. Okay? And this enolate is resonance stabilized, and they can react to make bonds at the alpha carbon. We're going to talk about that in a subsequent chapter. But ketones and aldehydes can react either at the carbonyl, and they can do chemistry at the alpha carbon. Okay, very important to know that you're going to get into some chemistry where you have to pay very close attention to the conditions. Okay. Technically, any nucleophile can add to a carbonyl and break the weak pi bond. But practically, there are some nucleophiles that aren't favored. So for example, if Jamie came into the lab and took her bottle of acetone and threw in some sodium chloride, she can push arrows to show this happening, right? It's real easy to show. A nucleophile attacks, breaks the weak pi bond, you end up with the alkoxide. However, the equilibrium does not lie to the product, it lies to the starting material. And way towards the starting material, so much so that she won't ever actually detect any product. Why is it that the equilibrium is favored on the left and not the right here? It's pKa. Remember that little paper I gave you at the beginning of class last semester from JOC about pKa and how it's useful, right? This is why. Remember, the equilibrium does not favor the stronger base. So here, chloride versus alkoxide, why is chloride the weaker base? How do I know that that's the weaker base? How do I know, Chance? How do I know that chloride is a weaker base than alkoxide without looking up in a pKa table? Well, I can look it up, but how do I know that? Is it? Okay, but how do I know it's a stronger base? How do I know that Cl minus is the weaker base? I know it because chloride, if I put a hydrogen on it, do I have a strong acid or a weak acid? HCl is a strong acid. That means that its conjugate base is weak. If I add a hydrogen to the alkoxide, I end up with an alcohol. Is an alcohol a stronger acid or a weaker acid than HCl? Weaker, much weaker, which means that that alkoxide must be a stronger base, right? And we know that the equilibrium is going to favor the weaker acid, weaker base pair, okay? And so that's what we have here. We have the weaker base, okay? So the halogen nucleophiles don't work very well in this type of a reaction, okay? But there are a variety of nucleophiles that work really well, okay? The hydride nucleophiles work really well. Why does the hydride work really well? What's the pK of hydride, approximately? Give me a rough range. Throw out a number. Way too low. That's water. Yep. Still too low. Getting better, though. 34, 35 is the pK of hydrogen. Okay? So hydrogen has that low of that high of a pKa, right? Alkoxide has a pKa of about 16 to 18, depending on the structure, right? So I would be going from hydride, which is a strong base, to alkoxide, which is a weaker base. So the equilibrium lies to the right. And these reactions essentially go to completion. Okay? We can also know that alkyl lithiums and Grignard reagents will attack a carbonyl carbon and make an alcohol in this case. The equilibrium lies to the left or to the right. What do you think, Maggie? The equilibrium in that reaction is going to lie to the left or to the right? To the right. And why does it lie to the right? What's the pKa of a Grignard or an alkyl lithium approximately? What do you think, Delaney? Where might a Grignard or an alkyl lithium be in pKa range? Not far off, 45 to 50, right? Yeah, they're really basic, right? The pK of the alkoxide that we get, 16 to 18. So the equilibrium lies to the right and way to the right. Okay? Cyanide is a pretty good nucleophile in these reactions. Cyanide will attack a carbonyl carbon because cyanide actually belongs to HCN, which is a weak acid. Okay? So HCN, the cyanide will attack the carbonyl carbon, and you end up with what's known as a cyanohydrin. Those are important molecules in apple seeds. We'll talk a little bit about that. These cyanohydrins are ways in which plants and animals have developed defense mechanisms. What do you know about cyanide? It's deadly, right? What do you think happens if I take cyanide, like sodium cyanide, and I mix it with HCl? What do you think I'm going to generate? I'm going to generate HCN, hydrogen cyanide, which is what they use in the gas chamber to put people to death, right? They actually take what look like flowers. I don't know why they do it. I think it's cruel that they do it this way. But they take these little things that are cyanide, potassium cyanide, and they press them into shapes that look like a flower. And they dump them into sulfuric acid into the gas chamber, and that's what's used to put the convicted individual to death. Okay, so guess what we're never going to have you be working with in the laboratory? You're not going to do any cyanide chemistry, okay? We've done cyanide chemistry in my lab a fair amount. You have to be very careful with it working in the hood, okay? You can also do reactions where you convert the ketone into an alkene. We'll be talking about that type of chemistry. We'll be talking about chemistry where we can take a ketone and convert it into a double bond nitrogen, known as an imine. We'll be talking about that chemistry. This is why you're seeing this slide right now, actually. It's because you can form an imine, as we call it. We'll be talking about how you can take a ketone and make an enamine, and how you can take a ketone and make what's known as an acetal. Carbonyl chemistry is rich. We have graduate courses based solely on the chemistry of the carbonyl functional group. You can get way into the weeds with carbonyl chemistry. We're going to limit it to these types of reactions for you all, okay? But the carbonyl group, in addition to the alcohol, the carbonyl group is probably among the most important functional groups in organic chemistry because we can convert it into so many things. If we look at this, let's look and see what's happening. We can make alcohols from ketones. We can make cyanohydrins from ketones. We can make alkenes from ketones. We can make imines. We can make enamines. And we can make acetals, all of which have biological relevance. Okay, so, and a very important functional group because we can get so many other functional groups from it. Okay? So you all know about the reduction of the aldehydes and ketones using sodium borohydride or lithium aluminum hydride. Mechanisms are essentially the same, right? You're going to end up hydride attacking the carbonyl carbon, breaking the weak pi bond. You get an alkoxide, which then picks up a proton from water or solvent, and you end up with your alcohol. Right? So why do I need two tools for this? Why do I need lithium aluminum hydride, and why do I also need sodium borohydride? Okay, lithium aluminum hydride will go all the way to an alcohol. That's true. So will sodium borohydride for an aldehyde or a ketone. No, I said you need both reagents in your toolbox, right? So why do we need two reagents when it looks like one will do? What's the difference? Which one's more reactive? Lithium aluminum hydride. Does it just reduce aldehydes and ketones? No, it reduces a lot of things, right? What does sodium borohydride pretty much so selectively reduce? Aldehydes and ketones, right? So sodium borohydride is more selective for aldehydes and ketones, whereas lithium aluminum hydride will reduce esters and carboxylic acids and those types of things. So you need multiple reagents in your toolbox, so to speak, right? How would we do the chemistry with sodium borohydride? You all did this the other day in lab. What did you do? You took your ketone, your sodium borohydride. What was your solvent? Anybody remember? You don't remember? You wasn't there? Oh. No. It was an alcohol, right? If you were to do lithium aluminum hydride, what solvent could you not use? You can't use water and you can't use alcohols. Why? It'll blow up. That's right. It reacts with the solvent, makes hydrogen gas, gets really hot, and goes boom. Sodium borohydride doesn't react with alcohols very quickly. It's very slow. Okay? And so it will survive those types of reaction conditions pretty easily. Okay? We can also add Grignard reagents. We've already talked about this, and get alcohols, right? The important thing about this reaction is that we're forming new carbon-carbon bonds, right? So you can take Grignards or alkylolithiums, add them to aldehydes, then upon workup you can get secondary alcohols pretty easily. If I had a ketone there, what would my product be? Would it be a secondary alcohol? It'd be tertiary. That's right. We can also add Grignards and alkylolithiums to esters. What do we get there? Tertiary. That's right. You would get tertiary alcohols. That's right. Okay. Cyanide will also add. The mechanism is pretty much so as you would expect. Cyanide, the carbon atom of cyanide attacks the carbonyl carbon, breaks the weak pi bond. You end up with an alkoxide intermediate, which then picks up a proton from hydrogen cyanide that's generated, and you regenerate your cyanide, which goes back and does another reaction. Okay? Cyanide has two atoms, carbon and nitrogen. Both have a lone pair. Why is it the carbon atom is the nucleophile and not the nitrogen atom? What do you think, Rose? Why is the carbon atom of cyanide the nucleophile and not the nitrogen, even though both atoms have a lone pair of electrons? It's definitely less electronegative. That's part of the answer. What's the other part? And it's the formally negative one, right? It has the formal negative charge. Nitrogen is neutral. But it also has to do with the electronegativity. So nitrogen's a little more electronegative. It's holding on to those electrons, whereas carbon's less electronegative. It's willing to share them a little better. So both of those things come together to make the carbon atom of cyanide the nucleophile. All right. I need you all to read ahead on this stuff for Monday, and have a good weekend. Go ahead and turn your, wait, did I say 5 o'clock today? I did. All right, so if you have it and you want to turn it in, go ahead and turn it in. If you want to wait until 5, you're more than welcome to turn it in up here on my box, on my door, on this office.